Let's get started. It's a pleasure today to welcome Jiayuan. He's a PhD student here at MIT, working with Josh Tenbaum and Leslie Kevling. Did this undergrad at Tsinghua University and spent a year, I think, being a visiting student at MIT. Jiayuan's interest is in developing structured knowledge frameworks for fast learning, and has done a lot of great and really interesting work in developing these frameworks that merge neural and symbolic representations for concept learning for reasoning language. We're really looking forward to hear about your work, Jiayuan.
Okay, so thanks, Harry, for the nice introduction. So hello, everyone. So my name is Jiayuan. I'm here, a PhD student at MIT, working with Josh Tenbaum and Leslie Kevling. So today I'm going to talk about this idea of building neuro-symbolic frameworks for visual concept learning and language acquisition. So let's first get started by looking at some my research interests. So many of my work has been centered around the connection between vision and language. So broadly speaking, I'm interested in this bi-directional relationship between vision and language. The first direction is how we can learn visual concept from this language. For example, looking at this image and the corresponding text, a man is riding on a horse. Can we ground these terms like a man or horse or riding onto the visual input based on just the natural language description? And later on, can we use the learned visual concept to answer questions regarding this image? For example, what's the man doing? Then probably the answer is riding a horse. I'm also interested in another direction, which is how we can learn language with the visual grounding. So for example, looking at this image and reading the corresponding text, a man is riding a horse. Can we develop, for example, this shows an example of like a relational graph that can be extracted from this natural language input, which says, okay, so there's a man and there's a horse, and the relationship between the man and the horse is riding. And I'm also interested in other types of language understanding. For example, how can we build parse trees based on some visual grounding? So today I'm going to talk about this bidirectional relationship between vision and language. So let's get started from the first part, which is neuro-symbolic frameworks for visual concept learning. Basically says, how can we learn visual concept from language? So we start from introducing the problem of visual concept learning. So given this image, as human, we can instantaneously recognize there are objects in this scene. And we can also associate various visual concepts with the visual appearance. For example, we can recognize the colors, the shapes, or the types of materials of this object. Such kind of visual concepts support us to perform reasoning over the image. As an example, to answer the question, what's the shape of the red object? We could first associate the word red with the color property of the second object and answer the question by querying the shape of the second object, which gives us the answer sphere. Beyond just answer questions, visual concepts also support visual reasoning of other forms. Like we can write image captions to describe the image that you are looking at, or we can retrieve instances from the data set that are associated with a specific concept of interest. In this case, the rubber spheres. So we first review some prior art for visual reasoning in the visual question answering setting. A typical favor of these models is to use an end-to-end neural network learning to predict the answer given the question and as well as the image. So essentially, there are two things to be learned by this neural network. The first part is the actual concept, that is the actual association between words and different visual appearance, like colors or shapes. The second part is the ability to perform reasoning, such as how can I count the number of objects. In such end-to-end learning framework, these two things are entangled with each other. So this resulting that the learned concept cannot be easily transferred to other tasks, such as to write image captions or perform instance retrieval. So I want to mention there have been recent success on explicitly incorporating concepts in visual reasoning. The NSVQA framework proposed by Yi and his colleagues is a representative work. The idea is to use a parsing subroutine to get the abstract representation of the image. It first detects all the objects in the scene and it extracts their attributes such as colors or shapes. And also, we incorporate a semantic parsing framework to translate the input question into a symbolic program. In this specific case, the question, what's the shape of the red object, will be translated into a two-step program. The first step is to filter the red object, and then the second part is to query the shape of it. Now, given this abstract scene representation as well as the symbolic program, we can just perform a symbolic execution step to answer the question. For example, in this case, the first step, filter red, we just select the object in this scene which has the red color. And to answer the question, we query its shape, which gives us the answer sphere. So I want to mention that during training, we need annotations for both visual concepts as well as these programs. This somehow restricts its application to real-world scenarios, where neither of the concept annotation for natural images or program annotation for natural language questions could be easily obtained. In this specific case, if I'm asking you, are animals grazing? So then if you want to have this NSVK framework to answer this question, you need very fine-grained annotations for visual concepts, such as not only animals or horses, but also what does it mean by grazing? So for the first part of my talk, I want to introduce you this idea of joint learning of visual concepts and semantic parsing. So essentially, there are two things to be learned in this loop I mentioned. So the first part is actually the concept annotation, the concepts for the visual thing, and the second part is the language part. So analogical to how human could learn this, we present this idea of use visual perception module learns visual concepts based on the language description of an object being referred to. And meanwhile, the learned visual concept would further facilitate parsing new sentences. So let's start from a concrete example. So given this input image, we can first detect the object in this scene and extract its visual representation for each of the objects. And next, we use a semantic parser to translate the question into a symbolic program which has a hierarchical structure. This is exactly the same program we have seen before. Okay, so it's worth mentioning that each of the concepts in this question, such as the word red, is associated with a vector embedding. And we build this Neuro-Symbolic Reasoning module, which takes the visual representation, the concept embedding, as well as the semantic program as input and give us the answer to the question. So we're interested in learning three things in this loop. The first part is actually the visual representation for various objects. And then the second part is the concept embedding for different words. So these two parts essentially forms the concept learning part. The third thing, we want to learn here is the symbolic program behind the natural language questions. So first, let's focus on how to learn visual concept via the symbolic reasoning module. Here, we assume that a latent program has already been recovered by the semantic parsing module. So the perception module learns visual concept based on the language description of an object being referred to. So starting from the first filter red operation, for each of the objects in this thing, we can use a small neural network to project its visual representation into a color space. And the concept red will also correspond to a vector embedding in this color space. Then we can compare the cosine similarity between the color representation of the object and the vector representation of red to classify whether an object being red or not. So in this specific case, so we will classify the second object as red. Okay, so the second object will become the input to the second operation, which is query shape. The next step is to extract the shape representation of the second object and compare it with the vector embedding of different shapes in the dataset. This might include cube, sphere, and cylinder. So again, we can compare the cosine similarity between the shape representation of this object and the vector representation of different shapes. So here, by comparing the shape of object 2 with cube, we got an confidence of 0.1, saying that it's very unlikely that this object is a cube. And we might say this object is a sphere and not a cylinder. So this will give us the answer to the question, which is sphere. In this neuro-symbolic reasoning process, all operations are just executed based on the similarity between object attributes representations and concept embeddings. So these things are all done in a latent embedding space. Thus, the derived answer will become fully differentiable with respect to the visual representations of objects, as well as the concept embeddings. During training, we use the ground truth answer as the supervision and a backpropagation process as the training algorithm to train these visual representations and also concept embeddings. So now we have seen how, based on the recovery program, we can learn visual concepts. Now we look at how the learn of visual concept can facilitate parsing new sentences. So during training for the semantic parsing module, which is implemented as by LSTM in our model. So for the semantic parsing, we sample multiple candidate programs from the parser. In this example, let's suppose that 2 candidate programs are sampled. We also show the semantic interpretation of each program in natural language, where the first program is what's the shape of the wrapped object, and the second program has the latent meaning of is there anything of the same shape as the red object. The next step is to execute all the candidate programs. So executing the first candidate programs based on the visual representation and also the concept embedding will give us the answer sphere, as we've seen before. So this is actually the correct answer compared with the ground truth, which is also sphere. So we would like to label the first candidate program as a positive example. And similarly, we can also execute the second program, which will give us the answer no, since there's only one red object in the scene. But it's worth noting that the answer no is incorrect compared with the ground truth answer. So in this case, we'll still label the second candidate program as being a negative example. For each of the parser programs, we use the execution result compared with the ground truth as some sort of a reward and apply a reinforced algorithm to train our semantic parser. So this will close the loop of joint concept learning and semantic parsing. In this framework called Neuro-Symbolic Concept Learner, these 2 modules are jointly learned only by looking at images and reading paired questions and answers. So no explicit annotations for visual concepts, visual categories, or the programs for natural language will be needed. To further facilitate this joint learning, we also draw inspiration from how children learn their visual concepts. So our model starts from learning object level concepts by looking at simple things and reading just simple questions. It then interprets referential expressions based on the learned object level concepts in order to learn relational concepts. Finally, the third step, we extend it to learn from very complex things and very complex questions. So our approach brings multiple advantages over prior art. First of all, if we just look at the QA accuracy on the standard testbed Clever dataset for visual reasoning, our model is able to achieve a state-of-the-art performance compared with other baselines. Moreover, we show that our model is more data efficient. Using only 10% of the training data, our model can reach the performance of 98.9% in QA accuracy, surpassing all the baselines by at least 14%. The Neuro-Symbolic Concept Learning framework can also be extended to natural images and natural language. Here, we show some execution traces of 2 simple questions from the VQS dataset proposed by Gan et al. The first question is to query the color of the fire hydrant. So again, we executed the latent program based on the same representation. The first filter fire hydrant operation selects the fire hydrant in the image. and the second operation queries color, which gives us the answer yellow. We can also do counting. In this case, we want to answer the question, how many zebras are there? So we first select all the zebras in the scene and perform the counting, which gives us the answer 3, which is correct. The learned concept can be easily transferred to other tasks. Here, we show examples of instance retrieval given object-level concepts and the relational concepts from the V2S dataset. So here we show examples of the retrieved instances of horse and person, and also relational concepts like person on a skateboard. In terms of accuracy, our model is able to achieve a comparable accuracy with other baselines for this general purpose visual question answering. So we have seen how such neuro-symbolic frameworks can support us to answer visual questions. And before ending this story, I want to briefly mention how we can also extend this idea to the domain of writing image captions for images or retrieve images based on the natural language description. And also, I want to mention the advantage brought by such frameworks. So the idea is very simple. So similar to the visual question answering case, here, in order to align an input image as well as a caption, which is a text describing the image, we want to have a factorized alignment between different components in the sentence with the corresponding region in the image. For example, in this specific case, the sentence reads, a white clock on the wall is above the wooden table. So we can extract some sort of relational graph based on the text description and align different parts, different components like the clock or the wall or the table with different regions in this image. So since we do not have object detector for many real world scenarios, we slightly modify this framework. Instead of grounding individual components on an image to the scene, we instead ground them to multiple pixels on several pixels in the feature map. So I won't go into very details of this work, but I want to show you some results we get. So this framework, namely the unified visual-semantic embeddings, is able to achieve a state-of-the-art performance on the task of image to sentence retrieval and also sentence to image retrieval on the standard testbed COCO. So both metrics are just standard metrics for image caption tasks. So another benefit by enforcing such kind of factorized alignment or very fine-grained alignment between the visual inputs and the text is that our model can have better robustness. So one way to test it is to generate adversarial captions in the following way. So given an image and its caption, we can extract its entities in this caption and also the relationship between them. We can then generate unmatched sentences by changing only a small part of the sentence, but will make the meaning of the sentence completely different. For example, in this case, if we change the first noun in the sentence, giraffes, into cows, then we'll get this sentence, 3 cows and the rhino grazed the trees. While this sentence has completely different meaning as the original one. But it's worth mentioning that if we add these unmatched captions into the data set, we will actually notice a significant performance drop for most of the image caption models. So, but notice that the model with the factorized alignment has the least performance drop. So here I want to mention another baseline method we employed, which is called VSEC, whose idea is to augment the training set with such kind of adversarial captions. The idea is sometimes referred to as adversarial learning. Here we show that even without explicit adversarial training, we can make the factorized alignment between visual, by making this factorized alignment between visual and the text, we can still get the robustness. So now let's move a little bit further towards a more general visually grounded learning system. So beyond, by this, I mean, what can we go beyond just answering about object properties or their relationships? We start from introducing some examples that requires the idea called metaconcept learning. So humans learn their knowledge about concepts through visual experience. Going back to this very first example shown in our slides, we can recognize the object and their properties such as colors and shapes and materials. But it is worth mentioning that beyond just visual recognition, humans could also understand the underlying relationship between concepts. For example, we can also understand that red and green describe the same property of objects. In this specific case, this is called the color. And we can also understand the underlying relationship between cube and block. First of all, they describe the same property of objects. And actually, they essentially mean the same thing, which says that they are actually synonyms to each other. So we can based on the learned visual concept, we can answer visual reasoning questions such as what's the shape of the derived object. But meanwhile, we can also reason about this meta concept. For example, in this case, we can answer the question: do red and green describe the same property of objects? So in this paper, we build a series of new data sets where we want to augment existing visual reasoning data sets with meta concept questions. For example, for the clever data set, we add new questions querying the relationship between red and green. For example, do red and green describe the same property of objects, or is cube a synonym of block? We also extended the GQ data set proposed by Hudson and Manning by adding very similar questions regarding the relationship between different concepts. We show two advantages of integrating concept learning and also meta concept learning. First of all, let's talk about how concept learning can help meta concept generalization. A quick example is shown on this slide. After learning the concept airplane and the concept plane from visually grounded question answering, one may conclude that airplane is actually a synonym of plane. This is because both concepts share a very similar visual appearance. In this case, we are doing this abstract reasoning to reason about the relationship between these symbols, which are actually not visually grounded. And we can do a similar thing for this concept red and yellow by learning red and the visual grounding of red and yellow from visual experience. We can conclude that so red and yellow actually describe the same property of objects. So there's one more direction I want to show you, which is more interesting. So look at this image, and if I tell you this image contains a cube, and if I also tell you block is actually a synonym for cube, then can you answer this question? Is there any cube? Sorry, is there any block? Most of us is able to do that because we can perform abstract reasoning between the relationship between the word cube and the word block. Another example is shown as the following. Is there any cube? And the answer is yes. And now I show you another example of cube. And if I ask you the following question, is there any cube in the image on the right? So the answer here is actually ambiguous because just looking at these two given examples of cubes, they are both green, this like greenish cubic objects. And the word cube might mean the color green or the shape cube, or probably just all green cubes. So this is like an intrinsic ambiguity here. So, but such kind of ambiguity could be resolved if I tell you something about the meta concept relationship between concepts. If I tell you cube and sphere actually describe the same property of objects, then you can reason about, so you need to classify object being cube or not based on its shape, but not its color. So this will give you the answer yes. So let's look into how we can combine or how we can extend the formally described neuro-symbolic reasoning framework for visual concepts to also reasoning about meta concepts. So we have briefly discussed how we can answer this like a visually grounded questions with a neuro-symbolic reasoning module based on the visual representation, concept embeddings, and also the symbolic programs of a question. Now, for these meta concept related questions, again, we can perform semantic parsing for these questions. In this specific case, do red and green describe the same property of objects? We can translate it into a program, which is to say we want to classify whether the red and the green has this like same kind of relationship. So this could be done by, again, a Neuro-Symbolic Reasoning module, which gives us an answer yes. So here, our implementation is very simple and straightforward. Basically, we use a small neural network, which takes the concept embedding of the word red and the concept embedding of the word green and classify whether they have this like same kind of relationship. So the reason why we can make this concept learning and meta-concept reasoning interact with each other is simply by sharing the embeddings we use for visual concept reasoning as well as for meta-concept reasoning. So here, you can imagine that the concept embedding used to classify whether an object being red or not is exactly the same concept embedding when we use to classify whether red and green describe the same property of objects. So before drawing the conclusion of this like a first type of framework, I want to state some limitations of our current system. So first of all, the recognition of in-the-wild images can be very difficult. So this includes, for example, detecting or segmenting individual objects or recognize their attributes. So on the right, we show a very challenging case of detecting and recognizing objects in very crowded scenarios and a very kind of like a cluttered background. So secondly, the visually grounded language generated by syntactic datasets, such as in the Clever dataset, still cannot match the real richness of human language. On the right, we show a challenging example for semantic parsing. It's something you will see deep in the wilderness. So this is a very challenging case for most of the semantic parsing frameworks that we have in hand. Thirdly, so far, most of the compositional reasoning, visual reasoning part have been centered around the compositionality of visual things and the reasoning procedure. However, it is still hard for a natural language understanding system to generalize to novel and more complex texts by leveraging knowledge learned from very simple but short ones. On the right, we illustrate this challenge. So after training on a subset of the Clever dataset, which contain only very short and simple utterances, simple neural sequence-to-sequence model for semantic parsing, for example, will easily fail to generalize to parse more complex utterances during tests, such as the one shown in the below. So to achieve such kind of compositional generalization as human could do, we should develop algorithms that are more aware of the compositional nature of natural language. So to summarize the first part of this talk, briefly, we present this idea of neuro-symbolic concept learning, which learns visual concepts from language with no annotation. It has several advantages. First of all, it has very high accuracy and data efficiency. And more importantly, it allows us to make the learned concept be easily transferred to other tasks by learning only from VQA experience. And also, the learned concepts support us to perform very robust reasoning over the text data. So there are two principles behind our framework. The first one is the explicit visual grounding of concepts through this neuro-symbolic reasoning framework. So here, we will make this visual grounding very explicit and in a factorized way, which means that we ground individual concepts to the object attributes or the object category, as well as their relationships. And also, to facilitate this joint learning, we introduce the idea of curriculum learning. So we have seen how the framework could support us to perform very transferable and very robust reasoning over the visual and the text data. Now let's look at the second part of this framework, which is called Neuro-Symbolic Frameworks for Language Acquisition. So here the goal is to understand to what extent the visual experience could help us or to facilitate us to understand language. So here I want to describe to you this idea called visually grounded language acquisition. So we again start from very simple examples of paired images and text. what can be discovered from this like single pair of image and text? So we have seen this image, and there's a caption reads, "A cat on the lawn." So if we only look at the single pair of image and text, the text might make only little more sense than a hash string of an image, right? Because there's nothing like this text is just like an alphabet. And however, we all know that natural language is so much more than just like a hash string. Why is that? So we argue here, two of the most important characteristics of natural language is its groundedness and also the compositionality. So how can we see that? So this could be seen if we have a pair of contrastive images and their corresponding captions. Assuming that we already have the ability to recognize visually similar parts in this image, which is a cat, and have the inductive bias that similar visual signals could be matched with similar signals in the text. So then we can probably draw this hypothesis that this text span, a cat as a whole, could mean something concrete that can be grounded on the visual input. And we can further verify our hypothesis by seeing more descriptive sentences of these images, because the only common word of these captions and the only common feature in this image is the cat. And here we can see, okay, the cat is staring at you, and the cat is playing with a ball. And it is worth noting that such kind of hypothesis, the cat as a whole means something concrete, actually matches with the hypothesis that linguistics has made for text constituents, which states that a cat as a whole functions as a single unit in a sentence. So we can verify such kind of linguistic definition or linguistic hypothesis by seeing more and more sentences. And some of them might have nothing to do with the visual grounding. So for example, here, we can also use this knowledge to understand sentences like a cat is chasing a mouse or a dog was chasing a cat. So here, I want to formally describe our the interesting research questions as the following. So given a large set of parallel image text data, for example, from the MS COCO dataset, can we generate linguistically plausible structure for the text? In particular, here we focus on the constituency parse trees without labels of nodes, and you only care about the structure here. So for example, on the right, I show the corresponding constituency parse tree of this input sentence, a cat is on the lawn. So here, I want to mention to people who are familiar with this field that, so although in general, the standard constituency parse tree are not necessarily to be binary, but for simplicity here, we just focus on just binary constituency parse trees here. So to tackle this problem, which is to generate linguistically plausible trees from parallel image and text data, we propose the following framework called visually grounded neuro-syntax learner, which is based on the hypothesis that concrete spans are more likely to be constituents. So the model, I will first give you a very brief look at the whole model. The model consists of 3 parts. The first part is, given the input caption, a parser will be employed to generate a constituents parse tree where we can get all the constituents in this sentence. And also, given the input image, we use an image encoder to encode it into a joint embedding space. And also, we can use text encoders to encode different constituents into the same joint embedding space. Next step, we will be using this joint embedding space to estimate the concreteness of an text span and use it as the supervision to derive the corresponding constituent parse tree of sentences. So I will describe the models like one by one. So first, let's describe how we can get a constituency parse tree here. So our constituency parse tree works in a bottom-up manner. So at each step, the parse tree will produce a score for each pair of consecutive words using a feed-forward network. In this specific case, we use a feed-forward network takes the representation of the word a and the word cat and produce a score, which says like 4.5. And we can do the same thing for this pair of words, cat and is and on and the, and the and lawn. The next step is we normalize the scores to get a probability distribution, which is a categorical distribution, which is defined over all consecutive pairs of words. And then we sample a pair to be combined at this specific step. Note that during inference, we can just gravely choose the one with the highest score. Okay, so to get the text representation for this new constituent, a cat, we simply perform a normalized sum of its children's embedding. And we will copy the words that are not chosen at the first step into this next step. The same procedure will repeat for another n-2 times to parse the sentence with n words. So again, we just compute the probability and combine them, and then again compute the probability and combine them. So finally, after in total n-1 steps, we will get this binary constituency parse tree. And also the textual representation for each constituent defined by this constituency parse tree. So then we consider the contribution of this image. And we will describe how we can build this joint embedding space and how could this facilitate the learning of the constituency parse tree. So the idea is simple. We borrow this idea called Visual-Semantic Embeddings, which is proposed by Kios et al. In 2015, which is to use hinge-based triplet loss between images and captions for visual-semantic embedding. So the loss term is defined as the following. So I will describe it part by part. So suppose that we have this paired image and caption pair, which is says like a cat is on the lawn. The first part of the loss function tells us now we sample a different image with the corresponding with the input image, but with the same caption, and says that this image should be classified as a force matching. And we can do the similar thing for the caption part, which is that we keep the same image and now we use a different caption as a negative example, and we ensure that there will be a gap. There will be a gap distance between the similarity between the matched image and the captions over the unmatched image and the caption. So this is a very standard hinge-based triplet loss. So now we extend this hinge-based triplet loss between images and captions to between images and the constituents. So here's some examples. So for example, the caption, the constituents a cat will match very well with the input image, while the constituents under will probably not match very well with this input image because this constituent might appear in many captions describing very different images. So let's see how can we define the concreteness of this image. So recall that all the loss terms between the image and the under should be larger, as this term under can appear in very different captions, which has nothing to do with this specific image. So we can define the abstractness of an constituent by its local hinge loss between the constituents and the image. And similarly, we can define the concreteness of a constituent just by flipping the signs of this definition of the abstractness. So let's see how we can use the estimated concreteness of based on this joint embedding space to facilitate the learning of constituent parse tree. So the overall learning object is very simple, which is we want to get a constituency parse tree which maximizes the total concreteness of the spans induced by this constituent parse tree. So basically, we choose the constituency parse tree that maximizes the overall concreteness of individual spans in this tree. So basically, we use the estimated concreteness as a supervision and apply a reinforced algorithm to optimize the continuous parse tree. So, but to really get it to work on real-world scenarios, we need to, there's one more thing that we need to take into consideration, which is the function word. So since that, it is difficulty to reflect the term of concreteness if we combine these two parse trees. Specifically, the word on, whether it should be combined with a phrase which is prior to it, or the phrase which succeeded. For example, whether in this case we know that the word on should be combined with this phrase belong, which is to its right. So, but notice that this is very difficult to be reflected in terms of concreteness. But there are some facts that support us to resolve this issue. So there's factor one, which is the word on is actually the head of this phrase on the lawn. And factor two, English is very highly initial, and so do many Indo-European languages. So highly initial means that the head of a phrase usually appear as the first or the initial term in that phrase. And the third thing, under the setting of visual grounding, most abstract words are function words. This includes things like propositions or determiners or complementers. So we propose a very empirical solution to this problem, which we call the head initial hypothesis, which will discourage abstract words from combining to the front. But instead, so we encourage an abstract word to be the left part of the corresponding constituent. So let's look into some results we get. So we first state the training and the evaluation dataset we are using. So we perform all the evaluation on the MS COCO dataset, which contains around 80K sentences for training. And so in MS COCO, so each image is associated with 5 captions. And we also present our results on the Modi 30K dataset, which has which has like a multilingual image caption and annotations, including English, German, and French. So we run each model for 5 runs and with different randomness, and we report the following 2 performance metrics. The first one is the F1 score, which is the average agreement with the ground truth parse tree. So since on MS code that we do not have like human annotations for these parse trees, instead we are using the Benapar framework down at Berkeley to derive the so-called golden parse tree. And so we perform the first evaluation metric is basically compute the average agreement between the derived parse tree and the parse tree derived from Benapar. And we also report the self F1 score, which is the average agreement across all pairs of models that are being trained with different randomness. So this evaluates how our model produce very consistent results after learning from a given data set. So we first look at these metrics for unsupervised grounded parsing. So we will compare our model with 2 groups of baselines. The first group is with so-called trivial structures, including just random trees. Basically, we just randomly combine every 2 consecutive words during the parsing, and also purely left branched trees. Basically, you always the tree looks like a purely left branching one, and also purely right branching one. And we also combine our model with prior art for doing unsupervised parsing based on language modeling, including PRPN and the auto neural SPN. So, and here, and finally, our models. We have our basic model, the visually grounded neurosyntax learner, and also the visually grounded neurosyntax learner with the high initial bias, and also the VGNSL model with the fast text initialization. Basically, you can imagine that it as it uses a pre-trained word embedding to initialize the embedding for individual words. So we can see that our model produced the very comparable or even better results than all the baselines, and use the fast text word embedding for initialization, boost our results to achieve the state of our performance. So the self F1 score also show that our model does the most, produces the most consistent output when several times on the same data set. We also test the data efficiency of our model, comparing against two strong baselines, the PRP and also RSTM. In terms of the F1, our model can achieve a very comparable result using only around 20% of the training data on MS COCO, while PRPN requires 100% of the training data to do a good job, while all the neurons achieve the best performance with only around 20% of the training data, but there will still be a gap between its performance and our best result. In terms of self F1, our model is able to achieve a very self F1 score with very little training data too. So we also extend our model to multiple languages, including English, French, and German. So in this multi-30K data set, so we want to mention that the number here are not directly comparable with the MS code data set because they're just very different data sets. But we can see that our model still consistently outperform all the other baselines across all the languages. So to draw a conclusion of the second part of my talk, in this part, I introduced this idea called visually grounded neurosyntax learner. It is a very simple, effective model for visually grounded language acquisition. And but not everything is perfect in our model. So there are definitely some limitations. So for example, right now our model only works for this very concrete domain, and we want to see if it is possible to extend to very abstract domains, such as the reasoning just about text. And also we might want to use more advanced perception module for relationships and quantities, so that we can do a better job for understanding the relationship, like the prepositions or verbs in natural language sentences. And also, it is possible to use more advanced parsing modules for handling non-continuous constituents. But it seems that our model has already done a very good job on this like a visually grounded language acquisition. But I also mention that, so our current progress is so far away from how humans could do. So here to also warm up this like overall environment, so I want to show you some examples and play a game with you. So if you look at this example of like a simple boards moving and maybe there are some like obstacles. So look at this video. Okay, so there's a red board which is moving in the thing, and probably it's going to achieve some goal. And I want to play it again so that you can see it more clearly. And here's the second example. Oops, sorry. Here's the second example. Okay, I will play it again. So now I ask you to look very closely at the third example. Okay, now maybe again. And now I'm giving you the following natural language utterance, which reads, the fat stacks the what with the blick on its way to the top. So here, so there are, let me count. So there are in total 5 words that are just like randomly created for this specific case. But I want to ask you to do this exercise in your mind, which is, can you figure out what's the meaning of the word fat, and what's the meaning of the word dex, and what's the meaning of what, and so on. So I will play this again, and I will wait for around like 15 seconds or something. So I think many of you is able to figure out, for example, the word fab is actually corresponds to the red ball of this in this thing, and probably the word corresponds to the green ball in this thing, and the blink should probably correspond to this like a war-like stuff, the obstacle in the middle of the thing. So how is this possible? So it seems that human is able to introduce to induce the novel meaning of 5 different words with just a single visual grounded experience and a single utterance. So this is the idea called syntax bootstrapping, introduced by Lila Gleiman et al. So the idea is very simple. So the idea is that humans are actually being able to use the syntactic relationship between different words in this utterance to help you to get the idea of the meaning of this word. For example, because the word fab appears as the subject to this word, to the sentence. So you will probably hypothesize that the word fab actually corresponds to some like animate object that is the subject that caused the event to happen in this specific scenario. So as we can see, our visually grounded and like a visually grounded language understanding module are still very far from this, because right now it is still just like mining some like patterns between the co-occurrence between some textual terms and the visual terms, but they are not doing real reasoning over the syntactic structure or the factorized structure of the thing. So we have still a long way to go in order to get a system that being able to do these fancy things like our human could easily do. So to conclude my talk, I want to draw some like a future direction that might be interesting to you guys. And so for the most part of my talk, I think most of the problems that I'm interested in are still just like a recognition based. Basically, we recognize patterns in the image, then we recognize the patterns in the text, and we try to connect them together with some like symbolic interface. But there are still many other things to do to really understand this natural language, to understand visual things, or to understand language. For example, I have briefly mentioned this idea of abstract reasoning about visual concepts. And also, humans are able to reason about events and to reason about the causality. For example, looking at the video on the right, we can answer questions like, what is responsible for the collision between the cyan and the metal cylinder? And probably you can give the answer, the collision between the cyan cylinder and the respirator. And also, humans could reason about physics. For example, in this specific case, so if I ask you, where is the purple sphere you have just seen before? One can easily understand that, okay, so because this like idea called like object persistency, so the if we remove this occluder, so the purple ball will be behind this occluder. So we can also reason about human intentions. So here I show you an example from the BQ data collected by Agrawal et al. 2015, which is, what's the purpose does the thing on the person's head serve? So the answer is actually shape. So this requires you to answer not only the relationship between different objects or subjects in this image, but also the purpose or the intention of different subjects. And the human is also able to reason with common sense. For example, if I ask you the following question given based on this input image, so which child is most likely to be blamed for ruining the composition of this photograph? So did you find it? So the answer is the child with his head turned. So I'm pointing to this little child here. So well, finally, I also want to draw some connection to robotic planning. So let's say, oops, let me maybe mute it. So the real goal of like understanding visual concepts, one of the final goal is to make it possible for us to build models that can interact with our physical world. For example, to understand, for example, something that we can give instructions to, like serving the cooked block, or find the green block, or stack the green blocks onto the purple one. So this allows this to achieve such kind of like robotic planning. So we need to build models that can interpret visual concepts from natural language interfaces and also understanding instructions and make sense based on our instructions. So this will finally give us a model that we can really teach with, that we can talk to, and we can really give them instructions and they can complete very complex tasks in real world scenarios. So finally, I want to show a very interesting example that I found which I think is a very great challenge to this like visual understanding, or how to go from recognition to understanding. So on the left, I show this examples called like the tic-tac-toe game. I think most of you should be familiar with this game. Basically, there are two players. The one draws crosses on this canvas, and the other one draws like circles on this canvas. And whoever got like two crosses in the same row or in the same column or in the diagonal axis will win the game. So you mentioned that it is very easy for us to build, for example, visual perception system to recognize like crosses or circles on this image, or or the grid of this image, right? So these are just like a very simple computer vision algorithm that we know we can do it. And it's also very easy, I guess, to train, for example, a reinforcement learning agent or a planning-based algorithm to play this game. But the real power of humans' understanding of this specific game is that we can make very flexible transfer to other scenarios. Like we can play this game not only on this like a Google page, but also on a blackboard with the chalks. So right now we learn. So suppose that we know how to write down something with a chalk, and then we know the rules for this game, and we know that all these abstractions. Then we can play this game on this chalk by only learn how to play this game from this like a Google page. So what is even more interesting, if we look at this video. So can you guys figure out what are this person playing? So basically, they are playing tic-tac-toe with this like a running game, right? So basically, I can say there are two. You can imagine that there are two groups of people, and they are not using like a cross or circles, but instead they are using different colors of clothes, I guess. And so basically, each group, the person for each group should first run towards this grid, this 3x3 grid, and then place the corresponding color on one of the grids, and whoever like get this like a tic-tac-toe game win. Whoever gets like a line or like a row of same color clothes will win the game. So it is very intriguing for us to look at such kind of challenges, which really need us to build very abstract models for understanding visual things or understanding games or understand like different concepts. So now I will end my talk, and I want to say thank you to all my awesome colleagues here, and yeah, and I'm now happy to take questions.
Thanks a lot, Jiayuan. Does anyone want to take a question? I have a question regarding the visual metaconcept learner. Yeah. I would like to ask you if you could get me an intuition on how we can learn how can learn that two colors are the same concept if visually they are different. Is it through the meta questions and answers, or is it because it learns a similar parsing program for questions involving two different colors?
So can you say that? Can you say the first one?
Yeah.
Sorry, I didn't hear you clearly. Yeah.
Yeah. Sorry. So the questions having to do with two colors, whether two colors correspond to the same concept. Visually, they are very different. So what is the model that allows it to tell that red and green correspond to the same meta concept?
Oh yeah. Yeah, that's a very good question. So so maybe let me go back to the slides of the corresponding framework that you are talking about, which is the understanding. Yes. So here we have a neural network based model to classify the relationship between different concepts, like whether red and green refers to the same kind refer to the same kind of property of an object. So actually we have these training examples to train this meta verified neural network. Basically we give it examples like okay, so red and blue refers to the same kind of property, and also cube and sphere, they refer to the same kind of property. So the neural net should be able to learn from these training examples and then generalize to unseen pairs of concepts. Yeah. So we do have the supervision during training for this a meta verified network to classify the relationship between different concepts. Yes.
I'm wondering if you have any thoughts on whether it would be possible to learn this without this supervision by basically learning similarities between the programs that you need to infer or something along these lines.
Oh yeah, that's another great question. So so yes, and in our paper we do not really explore this direction, but my thought on this will be actually in our paper, in order to enforce to enforce the such kind of a relationship like same kind or synonym, we actually make our visual semantic embedding space, like this concept embedding space, to be very geometric aware. Basically, so there are some sort of regularizations on the concept embeddings, saying that so if two concepts that are visually similar to each other, then their concept embedding should also be similar to each other. And if two concepts, they are mutually exclusive, for example, in this specific case, the word red and green, they are mutually exclusive, then this kind of mutual exclusivity should also be reflected in the corresponding concept embedding space. So I think by doing such kind of things, that it is possible to get a meaningful relationship between different concepts. At least you can classify for example, the hypernym relationship between all concepts, like whether for example, the concept animal actually covers all the possible cats, or some kind of a mutual exclusivity between concepts, like an object can only be red or green at once. Yes.
Thanks so much.
Hello. I had a question about how the model was trained before, when you had the parses like color and exists, and you outputted things like yes and no, but red and green. Is the output space for these different modules the same?
That's a good question. So I want to further clarify. Are you talking about this slide? Maybe the execution part.
Before. A second ago I saw it. I think you had one where there was two parses, and one had exists, and one had like the color.
Oh, I see.
Okay. Yeah.
Okay, I got it. So here, basically this is like a visual question answering task. So all the output, the output space is defined as like a predefined space of possible answers, which are just like a language tokens. Like you can answer sphere or true or false, or maybe different numbers. So basically, we're not enforcing any knowledge about like a yes or no is actually like a Boolean value. Basically, what we do is just say whether this answer string is correct compared with the ground truth answer string.
So for the when we're querying shape and it's looking at circle, cylinder, etc., it could have produced the answer yes and no?
Yeah, it is possible. I mean, at the very beginning of the training, so it's possible.
Okay,
yeah.
Cool. Thank you.
Thanks.
Right. Thanks so much, Jiayuan, for your talk. It was great hearing out your work, and thanks everyone.
Thanks.
Thanks.